Hello. In the last lesson, we talked about electric charges. In today's lesson, we will see how we can make these electric charges move so that we get an electric current. Now, what is a current? A current is made possible by something flowing. When water flows, you got water current. When air flows, you have air current. We call that the wind. Well, if you can make electric charges move, electric charges flow, we can get electric current. Now the question is, how do we make electric charges flow or move? Now tell me, what will make this object fall when I drop? Now, the object falls because there is a height difference. You see, an object falls from a high place to a low place. Now, when there is a height difference, we normally say there is a potential difference. There is a potential difference. So, potential difference is something that makes things move. Things move from a high potential point to a low potential point. So let's talk about electric potential. What does electric potential means? Now, an electrically charged object has an electric potential. The potential, what is the potential? You see, if I keep an object here, we say it has the potential to move. So, potential is the ability to make electric charges move. Electric potential is the ability to make electric charges move. A positively charged object has a positive potential, and a negatively charged object has a negative potential. Now, tell me, which of these is the higher potential? Is the positive the higher potential or negative the higher potential? Well, you know that when you want to make objects fall, objects always fall from a high potential point to a low potential point, or a place of higher height to a place of lower height. Now, in electricity, what is the higher potential? Is it due to a positive charge or due to a negative charge? Well, you know, we defined a test charge as a unit positive charge. And therefore, when you talk about motion, we are going to look at how this unit positive charge is going to move. Now, don't confuse here. In electricity, motion is associated only with the negative charges because they are the ones that are free to move. But when you define a potential, we are going to look at our standard positive charge. So, a positively charged object has a positive potential, and a negatively charged object has a negative potential. Positive potential is regarded as a high potential, and negative potential is regarded as a low potential. That means if you place a unit positive charge near a positive charge, it will move away from the positive and towards the negative, from high potential to low potential. So a positive test charge moves from a high potential to a low potential. Well, let me show that over here. Now, if this is an object that is positively charged, then this has a positive potential, and if this is a negatively charged object, well, a positively charged object has a positive potential. A negatively charged object has a negative potential. So if I keep a unit test charge, let me keep a unit test charge over here. If this is the unit test charge, which way is it going to move? It is going to move away from the positive and towards the negative. In other words, it's going to move from a high potential region to a low potential region. Just like an object falls from a bigger height to a smaller height. Alright, let's take that away. Now, a negative charge on the other hand, if a positive charge will move from a high potential point to a low potential point, a negative charge will then move in the opposite direction from a low potential point to a high potential point. Well, unfortunately, in electricity, it is the motion of the negative charges that constitute the electric current. Is that right? Okay. Now, a positively charged object, if a positively charged object is connected to a negatively charged object. Now, here I have a positively charged object. Now, the positively charged object is at a high potential, and a negatively charged object is at a low potential. What happens if you connect these by means of a conductor? What is a conductor? A conductor is something that has free charges in it. Free what charges? Is it free negative or positive charges? Free negative charges. So, look at this. This conductor has a large number of negatively charged electrons that are free to move. And when they are connected like this, these electrons will move from the negative to the positive. Now, from a low potential to a high potential. On the other hand, if positive charges were able to move, they would have been moving from a high potential to a low potential. Now, don't misunderstand here. What happens is when these conductors are connected by this conductor, an electric field, see, we talked about electric field in the last lesson. An electric field gets set up instantaneously in this conductor. And that electric field will make each of the free charges to drift. They will not move very fast. Each charge will drift. Now, negative charges will drift opposite to the electric field. Remember, the electric field is from positive to negative. Alright, so the electron drift is from negative to positive, which is opposite to the electric field. Now, the drift of electrons in this way caused by a potential difference between the two objects. Now, you can see there is a potential difference here. Is that right? Because the positively charged object is at a high potential and the negatively charged object is at a low potential. And the potential difference, it is the potential difference between the two objects that sets these negative charges move from the negative to the positive. If there is no potential difference, electric charges cannot move. Now, the potential difference between the two conductors is similar to the height difference that makes water to flow from a high point to a low point. So, in the same way, when you have a potential difference between two objects, one a negatively charged object, the other a positively charged object, and you connect them by means of a conductor, electric charges will flow or drift from the negative charge, from the negative potential to the positive potential, from the low potential to the high potential. So, alright? Now, let me see if I can show that to you. Give me a second. I will see if I can show that to you. Now, what I have here is, well, I have here, let me see if I can show you. I have here a little acid, and if I keep a copper plate, you see this is a copper plate, inside the acid, there is a particular property there. When copper is put inside the acid, electrons from copper will go into acid. Now that means copper is going to lose electrons. If copper loses electrons, it is going to have some excess positive charge. In other words, it is going to be a positively charged object. In the same way, if I have a zinc plate, now this is the zinc plate, if I keep the zinc inside the acid, zinc will take electrons. So what happens? In here, copper will lose electrons and the zinc will gain electrons. What I have here is, the moment I put these two, the copper and the zinc, this is the copper, this is the zinc. If I put them in the acid, let me see if I can get something to raise it up to show it to you. Alright, give me a second. Now, there is the acid there for you. And here is the copper electrode and here is the zinc electrode. I'm going to put it in there. And now, you can see I have actually connected these two using a conducting wire. And here I have a meter that measures. Can you see the meter measures? It is actually measuring the potential difference. If I lift them off, you can see there is no potential difference. When these are not in the acid, there is no potential difference. But when I put them back in the acid, you see there is a potential difference. There you are. Now, when these are in the acid, copper will lose electrons, zinc will gain electrons, copper becomes a positively charged, zinc becomes negatively charged, and therefore in the conductor that connects, that's the conductor I am holding here, electrons in the conductor begins to drift because of this potential difference and causing an electric current. Alright, let me put that away. Now, such an arrangement is actually called an electric cell. We can make an electric cell so that the cell will now produce an electric current. So let's now talk about an electric cell. What I just showed you is an electric cell. An electric cell or a battery, we generally call it a battery, but actually a battery is a combination of cells. So an electric cell or a battery is a device in which two metal plates which are called electrodes. In my demonstration, the copper is the positive electrode, zinc is the negative electrode. You see, because copper becomes positively charged, zinc becomes negatively charged. So a cell has two electrodes, a positive electrode and a negative electrode. And these electrodes are inside an electrolyte. The acid I used is the electrolyte. Now look at the diagram I have. This is exactly what I did. I have a copper plate and a zinc plate, and I put that inside dilute sulfuric acid, and I connected the two externally, and I measured the potential difference generated. And you can see the acid is called electrolyte. I want you to remember these terms. Now, these two metal plates are called electrodes. One is the positive electrode, the other is the negative electrode. And the acid is the electrolyte. So you got the electrodes, these two are the electrodes, and this is the electrolyte, the acid. And you have an electric current. You see, the electric current is caused by the flow of negative charges from zinc to copper, but the direction of an electric current is considered to be the direction of motion of a positive charge. You see, don't confuse it here, because we have chosen a positive charge as our test charge. Although it is the negative charges that are actually moving, the direction of an electric current is defined to be the direction in which a positive charge would move. So the direction of the electric current, therefore, is from copper to zinc. The chemical action between the electrodes and the electrolyte makes one electrode positive and the other negative. If the electrodes are now connected externally by a wire, the potential difference between the electrodes, I want you to be familiar with that term. It is the potential difference between the electrodes that makes electric charges move. Now, the potential difference will set up an electric field within the wire. It is the electric field which is responsible for the flow of the charges, and that will cause an electric current to flow in the wire. Now, we represent a cell by this symbol. Watch the symbol. You got a long, thin vertical line represents the positive electrode of the cell, and a short, thin line represents the negative electrode. So the thin, long line represents the positive electrode or the positive pole, and the thick, short line represents the negative electrode or negative pole. So in the cell that I assembled here, the zinc is the negative electrode and the copper is the positive electrode. Although the current is caused by the drift of electrons, now watch this again, I said that already. Although the current is caused by the drift of electrons from negative to positive, the direction of current by definition is from positive to negative. Why again? Because our unit, our test charge is a unit positive charge. That is why. Now, when a cell drives a current in a closed path, we have an electric circuit. So what I just showed you is actually an electric circuit. So when you have a cell driving a current in an external circuit, you have an electric circuit. Now let me show that one more time to you. If I can lift this and bring it over. I don't want to spill the acid. Now here you have the electrodes. Now this is the copper, that is the zinc, so the positive electrode and the negative electrode, and when the two are connected externally by a wire, and I have actually connected it to this meter, I have an electric circuit. An electric circuit is a closed path where electric current flows. Alright, I'm going to keep that away now. Alright. Now this is how we draw an electric circuit. This is a cell, and we allow the electric current to flow through an external load. You see, if you have a bulb connected, the bulb is the external load. Now this is something that we're going to call from now on a resistor. Alright, so we have the cell connected by means of a conductor to a load in a closed path. We have an electric circuit. Now the external conductor in which the current flows is called a resistor. So from now on we're going to call this a resistor, which has a resistance. A resistor has a resistance. In other words, it offers resistance for the flow of current. So this is our resistor. The current flows in the resistor. Now, a cell is connected to a resistor. Remember, by definition, the current is from positive to negative. So this is the direction of the electric current. Now, what is it that makes the current possible? Now, the current now exists because the cell has established a potential difference. It is the potential difference produced by the cell that is responsible for driving the current in the resistor. Now, when the cell is connected to the resistor, there is a potential difference between the ends of the resistor. You can see the positive of the cell is connected to the left end of the resistor and the negative is connected to the right end. So the left end of the resistor is at a high potential, the right end of the resistor is at a low potential, so the current flows from high potential to low potential. Current flows from high potential to low potential in the resistor. That's the way the current flows. Now, that's the point of high potential, you see, and this is the point of low potential. Now, remember, whether a point is a high potential or a low potential depends on where the cell is connected. This end is connected to the positive part of the cell. So this is a high potential. And this end is connected to the negative of the cell. This is a low potential. So the electric current flows from high potential to a low potential through the resistor. Okay. Now, let's talk about electric current again. Electric current in a conductor is actually caused by this drift or flow of electric charges, and we define it like this. Electric current in a conductor is a measure of the rate of flow of charges in that conductor. We have been talking about rate. Very often we use the word rate. What does rate mean? Rate is a ratio. So rate of flow of charge is the ratio of charge to time. You see? Now, if a certain amount of charge, we represent current by the letter I. So, if I have a cell connected to a resistor, a current I will flow in the conductor. And if a certain amount of charge Q coulomb passes through the conductor during a time t seconds. What is the definition of current again? It is the rate of flow of charge. In other words, it's a ratio of the amount of charge to the amount of time. So how can you write an equation for current? Current is the rate of flow of charge. I equal to Q divided by T, a ratio of Q to T. So I equal to Q coulombs divided by T seconds. Now, what is the unit of electric current? The electric charge is measured in coulomb, time is measured in seconds, therefore electric current is measured in coulombs per second, and we call it the ampere. The unit of electric current is the ampere. So what is an ampere? An ampere is a coulomb per second. Alright? Now, current is measured using an ammeter, and it is measured in ampere. Now, what is an ammeter? I have an ammeter here. This is an ammeter. You see that? You can see it is written out there. Now, it has got readings written on it, and depending on the position of this pointer, you can measure current using an ammeter. And we will do an experiment to measure current using the ammeter. Alright. Now here I have a picture of an ammeter measuring a current. How about potential difference? What is the definition of potential difference? I want you to listen to this and try and learn this. The definition of potential difference. Current flows in a conductor only if there is a potential difference between the ends. You see, a conductor, suppose this is a conductor, or what I'm holding is a conductor. In order to make current to flow in this conductor, I have to establish a potential difference. Now, how do I set up a potential difference between the ends of the conductor? Well, so all I need to do is connect one end of this to the positive pole and the other end to the negative pole of a cell. The end connected to the positive pole will be a high potential point, and the end connected to the negative will be a low potential point, and the current will flow from a high potential to a low potential. So current flows in a conductor only if there is a potential difference between its ends, because charges only flow from high potential to low potential. Now, a potential difference can be established between the ends of a conductor by connecting it to a cell. Now here I have the diagram which is called the electric circuit. This is the conductor, just like this, and this is the conductor. One end is connected to the positive of the cell, the other end is connected to the negative. That means this end where I'm pointing is now at a high potential, and this is now at a low potential. A current now will flow in that conductor, and the direction of the current will be from a high potential end to the low potential end. Now, potential difference between the ends of a conductor can be measured using a voltmeter. Now, I have a voltmeter here. This is a voltmeter. You can see V written there. Potential difference can be measured using a voltmeter. Now, I have also another kind of a voltmeter. If you can, let me see if I can make it visible for you. Now, this is a voltmeter. Well, let me see if I can turn it on. This is a digital voltmeter. Well, there you can read. All right. Now, if I connect this to an electric cell, let me see if I can connect it to an electric cell. Now, I have an electric cell here. I'm going to bring it over. All right. Now, here is an electric cell. I'm going to connect it to this voltmeter. That is that's positive. So I will connect it over here, and this one over here. Now, what does the voltmeter read? It says 6.04 volt. That means this electric cell that I'm using, this is actually a bike battery. Now, this has got a positive electrode and a negative electrode, and the potential difference between the two electrodes is 6.05 volt. Now, I did tell you that potential difference is measured in a unit called volt. Now, what is a volt? So, potential difference is measured in a unit called volt, and it is a measure of the work done in joules to transport 1 coulomb of charge from one end of the conductor to the other. Now, alright, now listen to me and understand this concept. Suppose I say the potential difference between the ends of this conductor is 1 volt. What does it mean? It means to transport 1 coulomb of charge from this end to this end, you need to do 1 joule of work. 1 coulomb, 1 joule per coulomb is called a volt. So, the potential difference between the ends of a conductor is measured using a voltmeter, and a volt is joules per coulomb. If the potential difference between the ends of this conductor is 6 volt, what does it mean? If there is a potential difference of 6 volt between this end and this end, it means in order to move 1 coulomb of charge from here to there, the work done is 6 joules. 6 volt means 6 joules per coulomb. A volt is joules per coulomb. Now, potential difference is measured using a voltmeter and is represented by the uppercase V. When a cell is connected across a conductor, a potential difference V volts appears across that conductor, and this potential difference will drive a current I ampere in it. Now, in order to drive a current in this conductor, what do? I connect it to a cell. What will the cell do? The cell will set up a potential difference between the ends of the conductor. And it is that potential difference which will drive a current in here. Now, the current in the conductor can be increased or decreased by changing the potential difference. You see, if the potential difference is high, the current will be high. If the potential difference is low, the current will be low. That means there is a clear relationship between the potential difference between the ends of a conductor and the current that flows in it. Now, the relationship between potential difference and current is given by this law. It is called Ohm's law. Now, here I have a conductor. I connect it to a cell. Now, what will it do? What will it do when I connect a conductor to a cell? When I connect a conductor to a cell, the cell will set up a potential difference across the conductor. And I can actually use a voltmeter to measure that potential difference. Now, it is the potential difference that is going to drive a current in there. Now, Ohm's law gives a relation between potential difference V across a conductor and the current I that flows in it. Greater the potential difference, greater will be the current. Now, according to Ohm's law, the ratio of potential difference V to current I in a conductor remains a constant. It means you increase the potential difference, the current also will increase. You decrease the potential difference, the current also will decrease. But if you divide the potential difference by the current, always you get the same value, as long as the conductor remains the same conductor. And that same value for the conductor is called the resistance of that conductor. So this constant, which is the value of V divided by I, the ratio of V divided by I for a given conductor will always be the same. And that value is what we call the resistance of the conductor, and we will represent that by the letter R. Alright, so this conductor has a resistance R. And how do you measure that resistance? The resistance can be measured by measuring the potential difference between the ends and measuring the current that passes through the conductor and dividing the potential difference by the current will give you the value of the resistance. Now, the statement of Ohm's law can be written. I'm going to write the statement of Ohm's law that V divided by I equal to R. The ratio of potential difference to current remains a constant, and that constant is the resistance of the conductor. Now, can you solve this equation for V? If you multiply both sides by I, we can now write this as V equal to IR. The potential difference between the ends of a conductor equal to the current in it multiplied by the resistance of that conductor. V equal to IR. Now, take a note of that equation. We will use that to solve problems. Now, V equal to IR is actually the same as V over I equal to R. Okay. Resistance of a conductor can be written. Can you solve for, well, we have already done that. R equal to V volts. Potential difference is measured in volts and the current is measured in ampere. So resistance is potential difference measured in volt divided by current measured in ampere, and therefore the unit of resistance is volt per ampere. Volt per ampere. And that unit, volt per ampere, is called the ohm, OHM. And we use the Greek letter, big letter omega. This is the letter omega. A couple of examples using Ohm's law. A light bulb has a resistance of 240 ohm when operating at a voltage of 120 volt. What is the current in the filament? Now, you are given the value of the resistance, you are given the value of the voltage, you need to find the value of the current. Now, can you recall the relation between current, potential difference, and resistance? What is the Ohm's law equation? Well, we have the resistance equal to 240 ohm. The potential difference is 120 volt. We need to find I. What is the equation we have? We have V equal to Ri. That is the Ohm's law equation. Okay. Now, can you solve this equation for I? We need to get I alone on one side. What do? Divide both sides by R. Okay. So, we have V equal to Ri, divide the left hand side by R because we need to solve for I. So divide the left hand side by R, the right hand side by R, and R cancels on both sides. You can see therefore I equal to V over R. Is that right? Yes. That gives me I equal to V over R. V I know is 120 volt. R is 240 ohm. So that is 0.5 ampere. Alright, another one. What is the resistance of an electric heater which takes a current of 15 ampere when connected to a 120 volt supply? Again, pick the values that we know. We have the current is 15 ampere, yes. The voltage is 120 volt. We need to find the resistance R. We again start with the Ohm's law equation, V equal to Ri, and we need to find the value of R. Well, that's what we did in the lab. What is R equal to? When you solve for R, we get R equal to V over I. So R equal to V over I, that will be 120 volts divided by 15 ampere, that is 8 ohm. Okay, let's do one more. Find the potential drop across an electric bulb if the filament that has a resistance of 240 ohm carries a current of 0.5 ampere. So what are the things that we know? We know the resistance R equal to 240 ohm. We know the current I is 0.5 ampere. We now need to find the value of V. And that's the simplest to do. V equal to Ri